Hello guys, you welcome to my channel. Today we are going to be looking at the second topic on the list of topics for the WAEC students that will be taking theory section of physics as soon as possible. In our last class, that is the first topic on nuclear physics, we talk about radioactivity. If you missed the class and you're watching this video, you can check the description box below to see the links to the video. We tackled enough questions on radioactivity and the topic is well explained. Thank you. Before we look into today's topic, paradox, that I'll be explaining in detail as well by His grace, I would like you to please assist me by subscribing on this channel. Help me to reach 100,000 subscribers as I proposed. Please, kindly comment on this video positively, like this video and share within your colleagues. Thank you. What is paradox? Before we look into the word paradox, I would like us to understand some prerequisite stuffs that is required for us. Now, what are those words? What are those prerequisites? Number one, we have to understand when something is a wave, what is a wave itself? What is a particle? When is something said to be wave? What are the properties of wave? Those things we need to understand before we go into the topic paradox. What is a wave? A wave is a disturbance that travels through a medium and transferred energy from one point to another without causing a permanent displacement of the medium. We have two classes of wave, the mechanical wave and the electromagnetic wave. The mechanical wave are those waves that require material medium for their propagation, while the electromagnetic wave are the ones that does not require material medium for their propagation. What are the properties of wave? Reflection, refraction, diffraction, interference, and polarization. The first four dimensions, they are peculiar to all waves. Anything called waves, they must have those four properties. While the last one, polarization, is only peculiar to electromagnetic wave or the transverse wave only. So transverse wave is an example or types of wave rather. So we are going to be talking about those things when we are talking about wave. Just note the properties of wave that I mentioned. Now, when something is a particle, for something to be particle, whenever something falls on it, it's going to do what? Absorb. And whenever it falls on something, it's going to emit something out of it. For example, if you throw a stone on your screen as you're watching me now, what will happen is that the stone will eject ink out of out of the screen. That tells you that the stone is a particle. Is that taken now? And if the stone is a wave, whenever you stone it on your screen, it's going to diffract, reflect, or show an interference. That is, it's going to show a wave properties: reflection, refraction, interference, diffraction. Are we together now? So if it show any of those properties, then stone is said to be a wave. But if it ejects something out of the screen or it emits something when you pour something on it, then it's going to be a particle. Do we understand the difference now? Now, with this, we can now tell if light is a wave or if light is a particle. Now, let's look into paradox now. When you say paradox, paradox simply means that something has a dual nature. When it has a dual nature, then it's said to be a paradox. For example, let's talk about light. Light's duality nature. When you talk about the wave duality of light, or the duality nature of light, whichever one, it simply means that light acts as a wave or as a particle. That is what we call the duality, wave-particle duality of light. Wave-particle duality of light simply means light can act as a wave and also act as a particle. That is what it simply means, and that is what we want to talk about. Now, let's quickly look into that. When we say light can act as a wave and also act as a particle, what is light? A light is an electromagnetic wave. A light is an electromagnetic wave. Let's look at the wave theory of light before we now consider its particle. If light can survive the wave theory with some experiments, then we can conclude that light is a wave. And also, if it survived the particle theory, then we can also say light is also a particle. Can we go on now? Let's look into that. According to the Maxwell theory, so I want to talk about the wave theory of light. The wave theory of light. Now, when you talk about the wave theory of light, according to the Maxwell theory of electromagnetic radiation, it states that for all electromagnetic radiation, there exists an oscillating electric field and magnetic field. So, and light is an electromagnetic wave. So, we have that light is an electromagnetic wave that consists of an oscillating electric and magnetic field. Do we get this now? So, according to the wave theory of light from Maxwell theory of electromagnetism as well, we have that light is an electromagnetic wave that consists of an oscillating electric and magnetic field. How do they oscillate? Let's see. If I have a profile like this, this is y-axis, this is z-axis, and here is x-axis. Okay, I would like to play with color for better understanding. If I have this like this, and I have red that goes like this, okay, let this red be the magnetic field that is oscillating along the y-axis, along the z-axis rather. And I have I have this blue to be an electric field that is oscillating along the y-axis. Then the whole of the wave, they are propagating, that is, they are moving on the on the x-axis. Please get it cleared. And their velocity is given as v along the x-axis. I will take it again. We want to show that light is a wave. Then we assume by the theory of wave that light is an electromagnetic wave that consists of an oscillating electric and magnetic field as shown in this profile. The blue line, if you look at it, is oscillating like this, and the red light is also oscillating like that. And I told you the red marker represents the magnetic field oscillating along the z-axis, and the blue marker represents an electric field oscillating along the y-axis. Then the entire wave is propagating, that is, their velocity, the velocity of the entire wave is along the x-axis, and that is v like that. Okay, if you look at this now, this is blue, 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 like this. So I have red also to come like this. Okay, if I also look at that now, you will see that this is like this. So, and I have this to be here. So this will be like this. And this is like this, and this is like this. So kindly pay maximum attention to this. Thank you as you listen. So if you look at this now, this is electric field on blue, and this is magnetic field. You can see they oscillate like this, and the magnetic field also oscillate like this. At every instance on this plane, the magnetic field and the electric field are in order with the velocity. They are perpendicular to each other at every instance. Are we together? Like you can see now, you see that the electric field and the magnetic field, they are perpendicular. This is what we talk about when we are saying the wave theory of light. So this shows that light is an electromagnetic wave according to the Maxwell electromagnetic radiation theory. Are we together? Now let's quickly look at something. How can we now verify that yes, light is what? Light is a wave, since we have seen this. Then if light is a wave, then light must be able to show some characteristics of a wave, like the reflection, refraction, diffraction, interference, and polarization. From here, we can see that light has been polarized to one direction because initially it's supposed to be moving like this and like this. Are you getting it now? But you can see it has been streamlined to one direction, but that might not be clear to you right now. Now, let's quickly look at another one that can be very clear to you, and that would be experiments of single slit and double slit. Now, let's look at that. If I have this, the Young double slit experiment can be used to prove that light is a wave. Let's first of all consider the single slit. If I have a screen like this with an open, when I say slit, it means what? A slight opening. So, and this is what? Light. You know, this is going to serve an obstacle as light travels on a straight line. So, whenever a light what? Hit an obstacle, something will happen. Reflection might happen, refraction might happen if it moves to another medium, and when it's bent around that obstacle, that is what we call diffraction. So because of this small opening, light is said to bend around this obstacle, and this is what we call what? Diffraction. So light has diffract in this place now. Diffraction. So if light can diffract, then it is what? It is a wave. Okay, let's see if light has another property that it can show. Let's consider the double slit experiment. So this is an opening and this is another opening. So if this is light wave that is traveling like this, so I have this place to diffract like this, and here also diffraction will take place. So this has shown what? That we have what? An interference in this region here. This is a destructive interference. If you can look at that, these are what? Dark fringe. These are dark fringe. And if you look at this region where I have my blue marker, we have a constructive interference. The interference is another property of light. Hence, light can be diffract and light can also show and what? Interference. Hence, light is said to be what? A wave. Now that we have shown that light is a wave, now let us show that light is also a particle. For us to show that light is a particle, then we have to consider the particle theory of light. What does particle theory of light state? The particle theory of light states that what? Light consists of what? Of some distinct what? Photons. It consists of some distinct particles known as what? Photons. And those photons, they are what? They are packets of energy that is given by the Planck equation, E equal what? E equal hf. So this is what we are given, okay? And we are told that whenever what? The photon falls on a metal surface, is going to eject what? An electron from the surface. And this was proven by what? The photoelectric what? Effect and the Compton effect. These are the theories, these are the experiments, those two experiments, the photoelectric effect and the Compton effect. We use them to verify that yes, the particle theory of light is definitely correct. How do we use that? Let's quickly look at the photoelectric what? Effect. What is photoelectric effect? When you say photoelectric effect, it is when you flash what? A light on a metal surface, and that light is sufficient to eject electron from the metal surface. Then that effect of ejection of electron by the light is what we call what? Photoelectric what? Effect. Remember what the particle theory of light states. It says that light consists of some particles known as what? Photon. So when light falls on the metal surface, photoelectric effect says the light, if the frequency of the light is high enough, note, if the frequency of the light is what? High enough, that is the photons, if they have enough high frequency, they will be sufficient to eject an electron from the surface of the metal. Now, that ejected electron depends on the frequency of the photon. If that should be the case, when you increase the light of the when you increase the intensity of the light, enough electron are said to do what? To eject more. Let me break it down. It seems I'm rushing. Let's take it like this. When you say photoelectric effect, take for instance, if this is a metal and you flash light on this metal, remember, according to the particle theory of light, the light consists of photon. That photon has an energy that is given as what? HF. Now, if the frequency of that light is high enough, whenever the photon falls on this metal, they are going to eject what? An electron. So when they eject an electron, that phenomenon is what we call what? Photoelectricity. Are we together? And you remember we said for something to be a particle, whenever it falls on something, it must eject something out of it. That is, it must emit something out of it. Like you throw stone to your screen and it emits what? Ink out of your screen. It shows that the stone is a particle. Hence, if light falls on this thing and the frequency of the light is sufficient such that the photons can emit what? Electron from the surface of this metal, hence light is said to be a particle. So according to photoelectricity now says that if you increase the intensity of the light, that does not mean that what? Electron will be ejected. Are we together? The only criteria for electron to be ejected is for the frequency to be high, and that frequency that will be sufficient to emit what? Electron from the surface of the metal is known as the threshold frequency. I'll be talking about this when we are looking at photoelectricity in full topic. Are we together now? Okay, the theory still continues. Photoelectricity now tell us now that what? When light falls on a metal surface, for that light to emit electron, it must have what? A very high frequency. It means that what? The photon is depending on frequency. However, if the frequency is high enough, the increase in intensity will also result to an increase in the number of electrons that will be emitted. Remember, I want you to get this concept very clear. If you increase intensity and the frequency is not high enough, electron will not be ejected. But if the frequency is high enough and you increase what? Intensity, the number of electrons that will be ejected would also increase. That is what the photoelectric is explaining. So it confirms that yes, light is what? Light is a particle. Are we together? But those conditions must be satisfied before you can consider that. Okay, if that should be the case, let's look at another theory that we can use to confirm that of a particle nature of light, and that is the Compton effect. The Compton effect says that if you collide a photon, that is light now, light consists of photon. We have proved that with what? Photoelectricity. So quantum effect now is telling you that if you now fired what? A stationary electron with a photon, it will cause the photon to scatter such that the scattered photon will have what? A very large wavelength compared to what? To the previous photon. I'll take it again. The Compton theory also do what? The Compton effect rather also explain and confirm that light is a particle. And this is how it's proved its own. It says that if you collide what? If you collide a photon with a stationary electron, it will cause the photon to do what? To scatter, such that the scattered photon will have a very high wavelength compared to the initial photon before the collision. Is that taken now? Hence, we can also agree now that light is what? Is a particle, since it has shown what? The characteristics of what? Of particle. Now, how can we now determine that wavelength? That's what? Of the scattered photon. That is why we have the De-broglie what? Equation. Debroglie in 1924 postulates the what? Electron diffraction theorem. That is, electron and some other what? Small subatomic particles, they can also behave as a wave. Take it clearly now. Electron and some other subatomic particles and microscopic what? Atoms, they can also behave as a wave. And he let us understand by giving us an equation that we can use to determine the wavelength of the scattered photon. And let's look at that equation together. From Einstein postulates, I have that what? E. So Einstein equation is given as E equal what? MC square. And also we have that the Planck equation is E equal what? HF. So this is equation 2. Equation 1 is equal to 2. I have MC squared to equal HF. And this should be my third equation. Are we together, class? If that should be the case, I can recall that F is equal to C over lambda from the wave equation. You know, velocity is equals to frequency times lambda. Let's call this equation 4. Then we'll use this equation 4 to rewrite equation 3. Then I will have that MC squared is equal to hc over lambda. If I cross multiply, I have lambda, which is the wavelength, to equal hc over mc squared. This will cancel this, Abi. So I have that the wavelength of the photon is given as h all over what? mc. Okay, if we are now dealing, you know, the electron now has a speed that is approximately what? Speed of light. We explained that in the last video. Now let's say that we are now dealing with a microscopic what? Atom. That the speed is less than the speed of light. Hence, we can say that C is equal to what? V. If C is equal to V, then we have that lambda equal h all over what? mv. Mass times velocity. We call that mv is equals to what? P, where P is momentum. So the Debroglie wavelength is given as h over what? P. And this is what we call the Debroglie wavelength. Is that taken up? So if this is called the Debroglie wavelength, this is lambda, this is Planck constant, and this is what? Momentum. You may be asked that what is the significance of what? Of the Debroglie what? Wavelength. The Debroglie wavelength shows that what? A body of mass m, are we together, and is moving with velocity v. There is a way that we can relate the momentum of the body and the wavelength together, and the Planck constant. I will take it again. When you are talking about the significance of this Debroglie what? Equation, it simply shows that what? There is a relationship between the momentum of a body and the wavelength of a body using the Planck constant. In a nutshell, that a body can exist as a wave and also a particle. Is that taken up? Now let's look at some WAEC question on this. Okay, I have here with me question from year 2012, number 10. The question says, sorry please, the question says, explain wave-particle duality of light. Explain wave-particle duality of light. When I say you should explain the wave what? The wave-particle duality of light. This simply means what? Light can act as a wave and also as a particle. That is what they are asking you. Light what? Wave particle duality of light simply means that what? Light can exist as a wave and can also exist as a particle. You've successfully answered that question. And question B, the question says, illustrate your answer in 10A with observable phenomena. That is, you should have a proof to the answer you give earlier that wave can exist as a wave, light can exist as a wave and can also exist as a particle. And what is your answer to that? So I would like you to write your answer in this manner. So we have what? Light as a wave. As a wave. Or you write what? The wave nature of light, whichever one. So it reflects. So we have reflection. Light refracts. We have refraction. And diffraction. Polarization. interference. So these are what? These are physical phenomena that can show that yes, light is a wave, because light can reflect, light can refract, light can diffract, light can be polarized, and light can be interfered. Are we together now? So the second one, which is the particle nature. The particle nature of light. The particle nature of light. Light can what? Light consists of what? Photon. Light consists of a photon, and we say light can be absorption. The absorption, we have what? The emission. So are you seeing it now? We have what? Absorption, emission. Are we together now? So this shows what? This shows the particle nature of light. Is that taken down? And also, light can also radiate energy. Let me put that. Radiation of energy. All these are what? The physical phenomena that light is a particle. Do we get this now? So you successfully answered that question. And in year 2015 number 7 states, write the De-Broglie equation. Write the De-Broglie equation. What is the De-Broglie equation? We just finished proving it now. You don't need to prove it. The question just says write it. So the De-Broglie equation states that what? Lambda is equals to Planck constant divided by what? Momentum. Where P is equals to what? mv. Hence, you have that lambda is h all over what? mv. So you can define each constant there, where what? Lambda is the wavelength, h is the Planck constant, m is mass of the particle, and v is the velocity of the particle. Hence, p is the momentum of the particle. So you successfully answered that question. That is what they're asking. So next thing, say what? Explain the significance of the equation. What's that? The significance of the equation is that what? A body can exist as a wave and also exist as a particle. Or you can say the significance of the equation is that there is a relationship between what? The wavelength of a particle and what? Its momentum, using what? The Planck constant. Is that taken out? So this will mark the end of the class today. But before I mark the end of the class, what are the likely questions that they will be asked you under this? Because these are the questions that frequently repeating itself. But what if they want to ask another question on this? You may be asked that what are the theory that verify what? That verify or confirm the particle nature of light. We have what? The photoelectricity, the quantum what? Quantum effect, and the electron diffraction. Are you getting it now? And also Davison and Gamma that confirms what? The electron diffraction in 1937. We can also use their experiments to show that. Is that taken now? So those are the theory that we can use to back that answer up. And when they ask you what are the theory to confirm the light wave, the wave nature of a light, then we can talk about the what? The single slit experiment and the Young double slit experiment. This will mark the end of the class today. In the next class, we are going to be looking at photoelectricity. Then from there, we'll move to AC circuits, then basic electronics before the commencement of your exam. I'm able to cover some other topics like the elasticity, projectile, simple harmonic motion, vector, and scalar. I'm going to drop their link in the description box below for each and every one of us to benefit from them. Thank you as you come and watch and like this video. Kindly share within your friends and don't forget to subscribe. Have a nice day.